So, welcome again. 3 intense days, heart beating up, the PULSE Hackathon, it comes to an end. You just need to remember what we told you the first day. Have you enjoyed the experience? I don't hear anything here. Yes? Yes, that's cool. So let's say hello over there to the audience on the other side of the screen. We are happy to announce that you are going to introduce 4 of the teams, your conclusive ideas. The jury is here. This is like a thesis tribunal. I still remember mine and what my thesis director told me. Hey, nobody knows what you're going to tell. So you have your PDF here. You are going to express whatever the teamwork has concluded. And from there on, the floors will be yours. We are extremely happy at the University of Vigo, the QoPHI LAB, Applied Photonics Lab, that we will welcome always that you want to come back. Obviously, monodon by Navantia is an incredible research that you have seen how their people are. That's extremely important for teamwork. And from now on, we desire you all the best in your life, and let's get to the floor. So if you please, the first team, who's the representative to make the presentation? Let's give him a big round of applause, yeah.
It's very, very generous of you to say that we are going to give conclusions. Okay, so for our group, I must pre-confess that most of our work had to do with the channel model. It's what we spend most time on. So let's start with that. Okay, yeah. So the typical way of modeling the ocean or a water channel has to do with the relative transfer equation. There are 4 main ways of going through the equation since you cannot get exact solutions for it. The most used in literature is doing Monte Carlo simulations, but we were told that we should keep the hackathon spirit in mind, and that means that we have only 2 days to work on this. And I think that being mindful of the time was important, so we went for a kind of different approach, which has also literature on it, but it's not the standard, which is to use a small angle approximation. It's quite okay in the fiability of the results. It's not as good as simulating every single photon, which takes forever in a computer. And also, it's not Beer-Lambert, where you just assume that when a photon interacts with anything in your medium, it's going to get lost. That gives very inexact results with reality. So we went for the small angle approximation. The small angle approximation has also another advantage that we will see later, and it's the fact that you can do algebraic inversion with it. And not only you can get your bit error rate with your whenever you have selected your hardware and you have your power and everything, but you can also select like a bit error rate maximum, for example, and backtrack and see what power do you need. You can also see for each decibel difference in your link budget how many meters you are gaining or losing. So that's also quite interesting. A thing you cannot do normally with Monte Carlo because you will need to simulate each different situation. If you want to change the depth or anything, you need to simulate it again. Now we have selected what the channel model is, but we need to take into account what the bio-optic model we're using too. And we went with Haltring. We surely made sure that the jury knows that we watched the videos of the hackathon because Haltring is explained there. What are the advantages of Haltring? That you can model everything by only a single parameter, which is the surface chlorophyll concentration. That's very nice. It's very nice that with just one parameter you can get quite a good image of what your medium looks like. So basically for this, what we did is check literature. Haltring has its own paper. you have to check the formulas. Most of the variables are constants that are given. You have to use some other data, experimental data, to use tabular measurements. For example, for the plain water absorption, that's a tabulated measure that you can get. And with that, you get your formulas for absorption and scattering that you need to calculate the total attenuation. But there's one thing missing, because you only have the surface chlorophyll, like at depth 0, you have your chlorophyll concentration, but you're not going to put your link at the surface. So you need to know what chlorophyll concentration you're going to have at given depths. So for that, you need to create a vertical chlorophyll profile. For this, we also went for literature. We don't know much about this. So we went with widths, and basically the model seals depth. It searches for depth using the aphotic depth, which is basically the depth at which your medium has only 1% remaining light from the surface. And then it's basically a Gaussian expression. And now you get your distribution of chlorophyll, of your chlorophyll concentration in all the oceans. So now you have the basic ingredients with which you can, with which you have your medium. With that, you can calculate for your medium the absorption, the scattering, add it and get the total attenuation. I didn't say it, but we are using, introducing now, we are using a 520 nanometer laser in wavelength, absolutely standard in UVigo, because it's this range close to 500, 520 is the least absorbed type of light. Okay, now to the least enjoyable part, which was choosing the transmitter and receivers. For the transmitters, our motto was that brightness beats power. So we had the same as we did with the small angle approximation choice. We went for a middle point. We didn't want to have a single mode, because we have, with our choice, we have 20 times the power of a single mode. But we also wanted to have enough tolerance so that, we could account for the pointing error. So we also chose a transmitter with a wider beam. For the receiver, the main thing we had in mind was the problem of natural sunlight, because depending on the receiver you choose, and if you put your link at a shallow depth, you're gonna get a problem, and it's that the receiver is going to receive a lot of sunlight. It's going to interpret that the photons that it's receiving are the ones that you're transmitting, and it's going to saturate completely. So we also went for our initial idea was to go for a silicon photo multiplier. It has this problem. A basic pin diode isn't sensitive enough, so we went again for middle ground. Okay, for the link budget, what we did, I don't know who helped us with this, is to use to assume initially we are in free space optics and use the standard Friese equation, and then add our small angle approximation water channel loss, which is obviously different as the loss that you have, negligible loss you have in free space. Things we had in mind for the link budget. You have to apply corrections for some things. For example, particularly, you have to apply some decibel penalty for the fact that you have it's not a single mode transmitter. It's a wide beam, so you're gonna lose some of the signal. You cannot think that the lens is going to focus all of the light directly. And our last thing before being able to make some calculations is applying the particularities of our small angle approximation to the model. Why does small angle approximation work? Okay, the fact is that in water, which is different than in air, photons are much, much smaller than the particles that they're going to collide with. So most of the scattering that happens is me-scattering. When you have me-scattering, what happens is that most of the scattering that happens, redundant, basically goes almost straight forward. The coefficients that are normally worked in literature are 90–95% of photons that deal with scattering get to the receiver. So you have to take this into account, and the equation for the effective attenuation is that one. The only really interesting thing here is to, if you think about it, is to take into account that if you have very short distances in your channel, well, not like you can consider that the limit, very mathematical this, but the limit of your scattering is going to be 0. Most of your problems are going to be related with absorption. And on the other end, when you have a very, very, very long distance between the links, when there are so many points and molecules where your photons can rebound, your model is going to converge to Beer-Lambert. So basically, scattering is going to be more or less the same as absorption, and you're going to lose almost all of it. And so then we did the calculations with all that we had for our bit error rate and our range. We used a 10-meter depth simulation. Now you will realize that for clear water, our link distance is over 150 meters, which is, let's say, quite optimistic and not something that is recorded in literature. Benchmarks right now for UVigo are trying to get there. So this is a very optimistic situation. It's more optimistic than me yesterday at night at 3 a.m. thinking I would have this ready. But this makes sense. Why? Because first, again, we didn't use Monte Carlo simulation, so the error rate is higher. That's true. That's an acknowledgement of our model. And another thing that our limited time in the hackathon produced is that the only noise we really could consider heavily is sunlight, as I presented before. So there are a lot of interferences there that were not considered and that are put in the appendix as possible improvements for the future. Turbulence, alignment, and very wide, etc. With those errors taken into account, the link distances would be much, well, not much, but a little bit lower and more close to reality. This is the results. The difference between clear water and harbor water is very, very big. We have a very big coefficient of difference. It makes sense. And this is the part which we didn't, it was our team's goal to get to the part where we could show the real advantages of using small angle approximation, which is the fact that you can use a scaling loss. My dream would have been to even have a dashboard simulation, like a web dashboard simulation, in which you could change in live the depth or the sunlight received or everything, and your results changed, because it would have been very cool to show. A thing that the groups that did Monte Carlo couldn't do, but we don't have it. We didn't have enough time, and we don't know enough. So this was all. Questions are not welcomed, and will probably be answered with no idea. Thank you.
So thank you so much for your interesting, optimistic presentation. at 3 a.m. I was watching the rematch from Spain, so sorry, you were working. Any questions, please, the audience? If we got online on the streaming chat some questions, please let us know.
Thank you very much for no questions. No.
Yeah, you impressed the jury, but you know, there is always someone raising hands.
Yes. Can you go please to the device selection slide?
Oh, no. Transmitter or receiver?
Transmitter, please. Okay, here you have chosen this 1 watt laser. And what kind of modulation are you using?
What kind of?
Modulation for this.
No idea.
It's
My
on-off
team
key.
can-
On-off key. You were
can-
using on-off key.
Ah, yes.
Yes,
We're using
yes.
on-off keying.
Yes.
Yeah. Do I have to
My
explain what that is?
question
or-
is, how are you going to modulate this laser?
Who?
How? Are you using an external modulator or?
Team.
Yeah, you can ask.
Yes, no?
Yes,
Raúl,
sure.
please, come.
For this case, we already discussed with the rest of the group that there was no need on using external modulator.
Uh-huh.
So,
So you're going to turn it on and off
Yep.
directly with the drive.
yep.
And what is the switching rate of this laser?
Anyone else from the team?
I don't remember because we were trying along throughout these days from megabits to gigabits. So I don't really know the exact measurement.
If it's gigabits, please send me the datasheet because
No,
I
yeah,
need
yeah,
it.
yeah.
So.
No,
It's not.
this is all theoretical simulation. So I don't know.
Optimistic
Yeah,
theoretical simulation.
Okay.
I don't really know. No.
Is that it, please?
Maybe I thought that it was megabytes. Megabits, sorry.
Okay, just curiosity. Okay.
Thank you.
Please use a microphone. There's people in the line.
So, do you have some, I think, figures on the bit error rate and things like that?
Yep.
I think I saw. Yeah. No, this one, yeah. So, you have it there. It's 1 megabit per second.
Yeah.
Okay.
For the simulation.
So, yeah. Yeah, it's nice. I like also
I mean, 160 meters is optimistic, no?
Yeah. Yeah, but I mean, this figure is quite nice.
Okay.
I like it. I also the table that you have here on the document, the link budget seems reasonable.
Okay.
It's I would add some things, but it's quite nice. So really good.
Okay, thank you.
Congratulations. Yeah. No, I'm not. I did not finish yet.
Okay.
No, but no, it's good. So just to make sure, the simulations that you made, these are just like, it's more of a plotting of a formula more than a.
We did the model with Python.
That I don't care. I mean, this, for example, is not a simulation in the sense that you try to send something on that model. This is just the formula of the verb, one
It's just the formula
the error
applied.
function
Yes,
of the. Okay.
yes.
Okay, so no, that's just to be clear. So okay,
Okay.
that's all for me. Thank you. Congratulations. It's nice. Someone.
So thank you so much for your presentation. The scenario was optimistic, but you know, always take into consideration that the jury will ask for some other scenarios. So that's it for Team 1. Congratulations. Now it's time for Team 2 to get into the podium and introduce your presentation. You please come. Again, a big round of applause. We need some support. And this is your mic. Sí, claro.
Hello everyone, good morning. Um, Welcome to this event. We are the team 2, which is formed by Aroa, Ignacio, Hugo, Lionel, and me, who I'm Jaido. In this event, we are going to create or try to create a future with underwater communication. In our group, in our team, we have already get to a kind of a solution for this challenge, which is using two kind of different type of lasers. And in the case of the modulation, we choose the Manchester, and the receptor is a PMT. In the following presentation, we can see in the upper side the index of the things we are going to mention in this presentation. First of all, I want to mention about the problem constants, why we have choose to transmit or communicate in light instead of sonar, which is already developed. The main resource, as we have said, is the higher data rate, low latency, and fast link setup. Also, at the same time, we provide us directionality and physical security, and reduce acoustic interference and stealth, which are some kind of the issues that the sonar will give. And then also about the channel physics, we have also taken into consideration the 4 different types of water, which are the pure sea, the green ocean, the coastal, and the harbor. In that case, we have also put a table about the coefficients we have already choose from a paper, which are taking into account the chlorophyll density in the water, in the different types of water, obviously, the attenuation, the absorption, and the scattering. At the same time, also we have we have taken into consideration the Beer-Lambert law, which is formed by which is mainly depends from the absorption and the scattering, where the absorption is the thermal dissipation of optical power into water molecules and organic pigments, and the scattering is the directional photon diffraction by suspended mineral particles and organic matter. At the same time, about the protocols we have choose, there are the 2 lasers we have choose. The first model is the Nivea, is the Nietzsche one, with 550 nanometers, which is a blue color, more or less. It provides high efficiency in deep blue laser for CRISI. The second one we choose is the Osram, this model with 520 nanometers, which is the green color for the places which has penetrate chlorophyll bands, like in the harbor or the coastal. Also about the sensor, we choose the Massachusetts PMT, which gives a high bandwidth photomultiplier tube, offering us the ultra high sensitivity to capture scattered and severely attenuated photon packets. About the modulation, we choose the Manchester encoding since it has a self-synchronizing protocol, and also the crowd embed signal that prevents baseline drift over noisy. About why we have choose those color, we have already write the physics advantages of the blue laser and the green laser, mainly because, and also we have taken into consideration the security trade-off and the deployment. The main reason for those color is just for being having a good connection in the communication, and also like achieve a kind of intermediate security for our communication. And also about the channel model we have choose, and the simulation plan is that we get information source, we change it into an optical source with a modulator, and that by lens we will transmit the optical signal through a channel with, in this case, as I mentioned before, is the water. Receive the optical signal, the receiver will go the protected detector, the filter, which is the thermal noise, and the decision units. Also, in the last part, we have another diagram which can represent this model. A part of that, about why we have choose that modulation system, as I said, we choose the Manchester system, which is like a type of the OK, giving us like low energy efficient and a low cost. It's simpler than the others and easier to simulate. And also we have created a simulation in an app that in the simulation we will be able to simulate the different type of water, and at the same time the rates the data we will receive, like a beer rate that beats air rate. The distance we can also change it. And that made us to have the consideration about different lasers, different protocols, or any kind of changes we want to make in the future. The mainly change we want to implement in our future idea is to integrate an AI agent and like a chatbot in our system, where the user can just say what depth they want and the distance they want to communicate, and we will give them the best laser, the best modulation, or the best modulation we can assure through the system by several applications. As they say, the AI agents will analyze the sensor and laser database, compare the available specification and capabilities. And our team thinks that this feature will streamline the sensor selection progress and help users quickly identify the optical hardware configuration for their mission according to their needs. And that's all. We have the video that I suppose it's gonna be presented, and also please don't have any questions.
Thank you so much.
And
that's your app, right?
Yeah, that's the video where we can see. Oh, sorry. Where we can see some main like primary data. Here we can see like the data we will receive depending of the kind of machines we will use, like the sensor, the emitter, and the type of water. We can see here we can choose into several type of drone emitters. That is the laser, and also we can see we are able to choose between different type of water, coastal, harbor, with all the parameters, the distance, the deepness, and also the bits we want to transfer. And this will get automatically the other result. The only part is the theoretical beer, that sometimes it will get to 5, but it's because of the distance that are not, that it's really far. But normally it gets quite the data result are considered true. And also we have here like some analysis for the different data in graphics, and a map of about the head. It's not well done. It should be improved, but since we didn't have enough time, we haven't finished it yet. Here we can add different kind of lasers, and we can also change the data from the data sheet, and that will be easier to use. That's the sensor, the receptor. We also can add new sensor to prove and make more proofs.
Great, you convinced me. But I'm no one here. Well, thank you for your presentation.
Thank you so
I
much.
think it's time now for, yes? the round of question. Oh, it's part of the team. It's going to explain.
The idea behind this is you don't have to do anything by your hand. You can add a parser and you can download the dataset from Hamamatsu or whatever, and the app fill the data, the parameters, and whatever. Then you have a chat. That's the part of innovation. I can do it now, but you can add a chat and I don't know. I want a drone that go to 200 depth and Atlantic Ocean and whatever. And this do the simulation for you and tell you the, I don't know, some laser and some sensor is the option tool for your mission. You can iterate a lot with that and you can add, I don't know, 100, 100, 200 sensor and iterate so fast. That's the idea of the app. And I finish.
Great. Now it's time for people here in the audience, both on the streaming channel and also here, to ask questions in order to know a bit more about your solution. Now I understand the slide where they say, show the app. Now I understand it. So please, if there are any questions. Come on, don't be shy. Yes, here, David.
So sorry, it's my duty to at least ask one question. So in your channel model for low depth, have you considered the interference, because at the end you're using a visible light, are you considering the interference of the sunlight or not?
Can you repeat the...
Yes, it's like, okay, for high depth, you don't need to consider the sunlight, but in your channel model, have you considered for low depth the sunlight of the sun that is going to have? Not noise itself, can be interference. Imagine that you're very close to the surface, maybe the sun can blind your receiver.
At the first time, we think about putting a filter, but the time didn't allow us to do it well, and because of the problematic of pointing the laser well to inside in the sensor.
Okay, so you didn't put it in the formulas, but at least you think on it.
Yes, yes,
okay.
yes.
So, a good job. It seems quite nice. But I have a question. So you say that you use Manchester, right? So I see here on the document that you have like a small concept error. Like Manchester is the encoding, not the modulation. Okay, the OK is the modulation, but so that's I don't really know. You tell me. Do you make some simulation of throughput of megabits per second that you have? Do you have any? I don't know.
No.
Okay. Because in this case, you also have to make sure to take into account the Manchester thing, yes, because it's not transparent in. So do you know what implications does it have on the throughput?
Could you repeat, please?
So the Manchester encoding has a really important implication on the throughput, yes, okay, on the bits per second that you can change. So you have the self-clocking capability, that's really nice, but do you know what happens? And
no.
Okay, you get half the bits per second.
Okay.
So you lose 3 dBs of throughput always. So that's something that needs to take into account. And I mean, I know you have it, but just to make sure, like, what order of magnitude of power that you're using on the laser? The power of the laser, what? I know you have it on the...
It's in the video.
Yeah, but just to... Because I don't remember.
Depend on the laser. We have 4 or 5 type
Yeah.
of laser, and we
But
have one
what order of magnitude, more or less?
1 megahertz. And
Power.
One
500 megawatts.
Milliwatts.
Millibytes.
So half a watt up to
5,
5 watts.
1,
okay.
and 0.5.
Perfect. Okay. Good. The thing that I really liked about this is the block diagram.
Yes.
I was really pushing to the teams to make it, so it seems quite nice. So congratulations, I think it's good. The UI is good, the simulations maybe not the best ones, but I think you did a good job. So
Thank you.
that's all for me. If anyone wants to add.
Any further questions? Okay, so applause for this team.
Thank you.
I don't know if they stay until 3 a.m. as the previous one, but being optimistic as I am as a social science guy, I must say that first team impressed me because they present an optimistic scenario, and the second one, in one of their slides, they say the future is here. Also, you add the chat. That's cool in your app, mostly because you don't need to be shy. This is like a scientific congress. You need to challenge your thoughts, your ideas with your peers. That's number one. And number two, there are people here, jury people, right, that they were on the position a few years back. And it's challenging for us all to introduce a new idea and to be questioned. And we need to be ready nowadays to do so. So please, team number 3, it's time for you to take the floor. Thank you. Again, an applause for them.
Okay. I hope with this one, right?
Yes, and this is the light. So in case you need to, okay.
Okay, thank you. Okay, so for our implementation, we did a little research on how to sorry. So for our implementation, we did a little research on how to model a channel point to point, to later get the whole mesh of work systems, and for that it's not working. To pass the
Look here, this way.
Okay. Thank you.
Up and down, up and down.
Okay, thank you. And for that, we researched a model that take into account the extinction rate, the absorption ratio of clear salt water, and the scattering dispersion model. We did take into account the chlorophyll concentration on a blue and a green laser. We did implement a scattering Henry Greenstein model with the extinction parameter computing both the absorption ratio and the scattering ratio, and we did a ray tracing expansion of a set number of photons to compute stochastically the number of photons that reach the receiver. Okay, so we take into account the noise, both coming from the sunlight and from our devices, from the transmitter and the receiver. We take into account the thermal noise coming from the pin laser and the receiver, the shot noise, the background sunlight, and some random Gaussian noise that can appear. Okay, we we did implement or we did implement our simulation using a Monte Carlo model, and all the results were obtained stochastically. Why did we use a Monte Carlo? Because it's easy and does a lot of things, and cheaper than all other simulations. And these are the characteristics for the transmitter. We did implement a blue laser transmitter and a green laser transmitter with the nominal power between 1 and 1000 milliwatts with an OK modulation of 1 gigabytes per second of bandwidth. The receiver has this characteristic. We will get deep into that. And we did first a competition of the chlorophyll concentration in clear water, on how that affects the received power of the transmitters. And we did implement a Russian roulette Monte Carlo simulation. And we send between 25 and 6,000 photons per simulation. And this is going to be like a simulation debunking, because what we did is try to compute all the results stochastically. So for the first result that we wanted to show is the received power. The received power versus the distance of said lasers, because we wanted to get the most optimal result, and that's why we implemented. For the propagation model, we did implement a ray tracing model where every photon has an initial position, an initial direction, and it propagates, taking into account the scattering and absorption probability, and basically randomly changing the propagation direction, and then computing all the paths until they reach the receiver. And again, this is basically saying the same thing, because we like our results, so we wanted to show you for the green and the blue laser. And this is one of our first results when we tried to compute the maximum link distance in function of our transmitting power. So those are the results that we get for both lasers, and this is an interesting part, because for our simulation conditions, we took into account a set number, set chlorophyll concentration, and for that we needed to do a modeling of that number, and took the most optimal chlorophyll concentration that we consider. We also got the delays for the multipath impulse response modeling. The actual response of the channel in terms of loss versus the distance traveled. This basically the same thing, but in natural units. And compute the delays that that set distance is introducing to all the scatter photons. This is for computing the distance using a parameter like the bit error ratio. What we did is first compute the bit error ratio with a maximum likelihood decessor, and then utilizing the values that we got earlier with the channel response, trying to compute the maximum link distance, utilizing another parameter like the bear, and this is basically the limit. For another check-in, we did also a recount of the number of photons, the number of photons transmitted in function, and we get basically the same result. This is basically the same graph. I don't know why we have it again and again, and this is the channel impulse response that we have utilizing the ray tracing model only in this case 20 meters, and these delays that we have here are taken into account by computing the distance that there is between the unscattered ray, the photon that reached the detector unaffected by scattering, and the received photon that we got. Okay, so what do we get from all of this? Basically, we get that the attenuation is exponential. Our system is power limited, but not bandwidth limited. The bit error rate in our case is basically binary. Either we have no errors, or we have all the possible errors. Of course, we get that depending on the wavelength of the laser, the channel response also changes, and we get that around the 90 meter distance link. That's where we start to get the first errors in our system. We also this implementation is just for a point to point transmission. So what we like to do in the future is take the PIN receiver and make it an avalanche photon detector that doubles our reach, and with a lot less power. We have to compute a full noise model. We wanted to do a study about how the conditional modulation affects our system, get a full scope on the way of the possible wavelengths, and add something like misalignments, turbulence, sunlight in the sunlight interference depending on the depth, and the conclusions of our project, but were basically that we could compute a a channel response, and we could model stochastically using Monte Carlo simulation. And the one thing that we got is that for an OK and 1 gigabits per second bandwidth, we don't have a lot of coverage, and we also did a simulation of an APD and a PIN. We got a better result in the APD with much less power, and we need to take into account the wavelengths of the laser. And thank you for your time. And if you have questions, just go for it.
Thank you, team number 3. So now it's time for the audience to ask some questions. Yes, Baram?
Thanks a lot for the presentation, very detailed analysis and nice simulations. But I have a question about, you say that attenuation decays exponentially. You have it in the conclusion, but in the graph, it doesn't show that you can fit it into the exponential decay. Can you explain that graph, the distance versus the losses?
Yeah. For that graph, we basically did it stochastically. Basically taking the number of photons emitted and versus the number of photons that they reach to the area of the receiver. We compute that model in natural units, and we did how is it called? A linear regression to get the formula. We didn't put it. That's kind of for bad. But we get an exponential function of that.
Okay. Yes, thanks.
Can you please go back to the slide with the characteristic of the detectors?
Yeah,
the beginning.
Yeah. Nope.
Yes.
Yeah.
No. Yes. What is? Sorry, I don't understand. What is 1 milliwatt PIN gate?
In that case,
no, like no, I didn't do that. It's not my part. I'm sorry, it's not my environment.
Okay. I think that with that wording, what the that's the sensibility of the receiver. In the simulation, we put minus 30 dBs to get something like a harsh receiver and see how it affects the bit error rate. We did also a sweep on the different sensitivities and to see how they also affect the results.
1 milliwatt is quite a high power at the receiver, isn't it?
Yeah, that's why I also because we wanted to get a really optimistic power receiver, so we have a better understanding of how the bear evolves in our system.
Okay, thank you.
Yes, 2-3 questions.
It's good because I have a question related with this. I can see you have the characteristics of the transmitter, receiver, etc. But have you checked on actual components of the shells that you can?
Yeah, I mean we didn't put the name of the components, but for the laser models we have the PLT5 500B. No, pardon. Sorry, 5 to 520B. The 520B. I mean, that's for the green laser, and for the blue laser we have the PLT5 450 B. I mean, those are commercial lasers.
And for the receiver also?
For the receiver is the S54, sorry, is 549302.
Okay, but it's good to put in the presentation and
Yeah,
also
yeah.
the documentation. Thank you.
Yeah.
Yeah, thank you. So thank you, and really nice presentation. And what I really like about the document is you actually answered the why these things. And okay, so first thing, why did you choose 1 gigabit per second and 100 milliwatts? That seems too low of a power and too really high of a bandwidth.
I mean,
so
because we wanted to reach how's it called? Compromiso. I mean, a commitment.
Yeah, but okay, but
no. I mean,
if you really get those distance with that, make it real. You will.
I mean, we make an ideal case of clear water with not really a lot of currents in it, with a set QoPHI value.
Another thing on the simulation, the 25K photons. Why is that?
The 25?
Yeah, you use like 25,000 photons to simulate that.
Because
like a quick estimation is 10 to the 18 photons per second at 100 milliwatts of power. So
yeah, I mean,
but that's it. Yeah.
No. I mean, because we found a model with that number of photons, but we wanted to do because we thought with a ray tracing model, they were going to be computationally expensive. So we wanted to reach another commitment of reducing the computational power of the simulation and adapt the model. That's why we also do a Monte Carlo Russian roulette to 14
orders of magnitude.
So what? 14?
I mean, yeah, 14 orders of magnitude between what you simulate and what 100 milliwatts.
Yeah, I mean, because this is
okay.
This is like just a first approximation simulation.
So thank you so much. I'm sorry to be a bit rude because we are almost in our schedule, but I think that's great. Please, let's thank team number 3. Thank you for your presentation. Now it's time for team number 4. You need to understand, please, came to the podium, team number 4. We are on a schedule, but we depend on our chronogram and we need to take that into consideration. And obviously, then on the coffee break, we will have time to discuss any kind of results. So team number 4, please.
Okay, 1 second. Everything okay? What is
the mic? You need the mic?
No, the mic. No, the controller.
Here.
This is the controller.
Up and down and lighting. That's the light.
Okay. Hello. Hello. Good morning. Good afternoon. We are quite in the middle. We are group 4, and we are going to present our solution to the problem involved in the PULSE Hackathon. What? The down button.
Yeah.
Okay. We are team 4, formed by Sergio Gándara, Adrián Garrote, Antonio Cano, and Daniel Quintana Alonso. Here we have a little bit of the implementation we've done in these 2 days. You can see it can seem a lot or not. It can be hard anyway. Okay. This is with a lot of thinking and implementation, we have decided that the right way to start doing this was trying to model the physics channel we want to use to do the simulations. Determining the modulation regime, we are going to do the transmission, and the goal is to receive a good SNR and see the maximum capacity and the actual bear we can get. And sleep, not a lot. I'm gonna change the order because it's better like this. Okay, we have based the physical model channel in the SNR, signal noise ratio, to see how much signal we can get. First, that the noise kills the signal. This is a simply not realistic 3D to understand the concept we're trying to explain here in the model. We have the direct transmission and the diffuse transmission that we are getting by the absorption and the diffusion of the light in the water. Here we have the transmitter, and here we have the receptor, and we can see how even the direct ray is slowing down, getting lower by the noise and the diffuse. Here I'm going to explain quickly the equations. I put the time. Okay. To get the SNR, we need that's the received optical power that the sensor receives with the receptivity of the photodiode, and we have the total variance of the noise, the summatory of the noise that we have kept in mind. We have kept in mind the thermal noise and the shot noise of the system, because we try to keep in mind also ambiental light noise and turbulence, but it had quite difficult equations that we were not able to add to the model in time. With that, to get the received power in the sensor, we do it with the power transmitted by the transmitter, the efficiency of the transmitter and the efficiency of the sensor, and the total transmission we are getting, which we are going to explain now. The total transmission is getting by the direct transmission and the diffuse transmission that we could see in the image. To get the direct transmission is just the minimum, because it has to be less than 1 from the diameter of the optic sensor of the optic lens of the sensor, and it's too many information. And that's the diameter, that divergence of the ray as of the transmitter, which we can get the radio of the divergence is getting the ray in the direct transmission, and here we get the extinction coefficient of the water that affects our transmission, and the distance again. That's the distance we are putting the transmitter and the sensor. And we have the equation for the diffuse transmission. We have also the diameter of the sensor. We need to know how much light we are getting from all the diffuse light is arriving at the sensor. And here we have the diffuse. The expansion of the diffuse light, how this the diffuse light is expanding through the channel. We also need to keep in mind that the LDIF, that is how that light cloud is attenuation through the way, because that light is also subjected by the absorption and the distortion of the light, and that's its equation. This is the dispersion angle, and we get the median value of the same with that, and we are starting to see the A and B that are and C, A and B, and the absorption coefficient of the water, the dispersion coefficient of the water, and the extinction coefficient of the water. That is the sum of both, which explain fast here. To do the simulation, we take from the wavelength of the transmission, we take four constant values. We choose 532 nanometers, and we take this from a paper what they use. This is the base absorption of light of the pure water, the base dispersion of the pure water, the chlorophyll absorption constant, and the empirical exponent of the chlorophyll. We get A from the base absorption, adding the absorption of the chlorophyll. The chlorophyll, we take the value. We take the value from this map of Copernicus map from the European Union. Here we can see that we can get the chlorophyll in order of the depth of the ocean in any point we want. We could also get the temperature. We tried to code it in the simulation, but it was quite difficult, so we get it manually. So with the chlorophyll and the data we already have from the paper, we can get A. With A, we get C. That C can be a absorption coefficient and dispersion coefficient, but it can be also taken with the base dispersion coefficient and the C particulate, which has this formula, and later we get from this with this page B and the coefficient, and with that coefficient we do all the simulation and the data you are going to see now. Let's do with my partner. This one.
Well, that was quite a heavy math model, so we are going to step back from the high resolution math, and we are just going to keep it simple from now on, but just keeping a bare minimum explanation of all the theoretical concepts that are involved. So we have established the first freeze model that we are using to analyze the channel to get the SNR. That was our first and foremost goal that we achieved. Then, after getting the SNR, we thought, well, we have to modulate this. So we chose the OOK modulation, that's on-off modulation, as everyone here has been doing. That's because it's the simplest modulation. And, well, it has a theoretical equation to calculate the bit error rate, so that's quite nice. And the good thing is that if we manage to get the SNR from our model, that's an analytical model, mind you, then the bear is right there in our hands to grab. And we got this equation from that paper there. Well, and for the modulation, we ran a random simulation of bits for our returning 0 OOK. And there you're seeing, I think that's the point, yeah. This is the OOK modulation, and that there that you are seeing on the yellowish line is what we should receive because we are considering an additive white noise channel. We are talking about the noise later in the presentation, but we simulate the bandwidth with a low-pass filter, and this is what, statistically speaking, we should get or we should expect in the channel. So after that, we simulated as well the featuring and equalization because, of course, we had to decide over what bit is that we're receiving. So we use LMS, as you're seeing here, the LMS estimator to estimate the bits. And we are talking about that later in the presentation because we think that there is a margin for innovation with this one. But, well, basically, after simulating the modulation, we tried to get the eye diagram. We did not get the eye diagram because we wanted to extract a first conclusion or utmost important goal from this. Of course not. We're just interested in looking at, well, the quality of the channel. So, basically, this is like a very somber explanation of what you can extract in terms of information in the eye diagram for those of you that are not acquainted so heavily with transmission theory. But it reduces to knowing basically three things. One is that the eye diagram is basically plotting the transitions between the levels that we have, because we have only two symbols, because that's okay. We are just going to have two symbols, sorry. So the most important thing that we have to take care about is that these transmissions, as you see, are quite poor. That's because the eye, that's this structure of here, that's hence the name, it's not as open as we would like it to be. But that's okay. We know the channel's bad, and we know that we cannot hope to get such a good model as, for example, a cabled optical communication. So for comparison, let's move quickly with this. This figure we extracted from another paper just for reference. This is a much desirable outcome that we'd have, and this is more similar to maybe this and this. And this is just saying that with heavier attenuation and poorest channel, we cannot get such a good transmission. That's all the conclusion that we can extract from this. We are not extracting any other metric from the eye diagram. We just thought it was nice to have in the presentation. That's for the questions that are going to pop up later. And well, this is a diagram of the system, of the entire system. So we basically ignored all of the surrounding stuff of the system, and we stayed only with the modulation stuff, that was the OK that we just talked about, and the optical source, the channel that we are going to talk about with the noise things, and the optical detector, and well, the demodulator that we did not bother to mention because we think it's more important to have in mind the optical components of the system. So about real devices that we thought that were the most appropriate, we looked about like 5 papers in total, and we extracted a set of devices that, after careful but fast consideration, because it was 3 in the morning, we thought of these components. So you can see a small set of parameters here that those are the ones that we are taking into consideration with our simulations. And well, this is an avalanche photodiode that we are using as the receiver. And this is the optical emitter that, as my partner talked before, we are using a 532 nanometers emission. And again, there's a small set of parameters here that you can see that, well, we use to model the transmission. And this is the transimpedance amplifier, and this is the equation that conditions all the transmission, because it's the expression that conditions the bandwidth. So we extracted this from the datasheet of the OPA that we're using for the transimpedance amplifier. And the transimpedance amplifier is, of course, again, from another paper. So about the channel, again, white noise additive Gaussian channel. Nothing new, and the reason why we're using this channel is because we can get the maximum theoretical capacity straight away, and that's very convenient. And other assumptions, well, the wavelength, we talked about that. The distance is our parameter that we are going to vary to see the plots, and the depth equally, but for brevity of the presentation, we just decided that the depth was best to keep at a constant. But we can change it in the simulation if we liked to. And the temperature, that's another important data point. Well, for the noise, well, we talked about this a few times altogether, but basically we keep in mind the dark noise variance, the thermal noise, and the shot noise. These talking about practically all receiver bounded noise sources. So what are the results? That's the interesting stuff. Well, we plotted this one, but because there's not so much resolution in the projector, you maybe have difficulties seeing the numbers in the plot. But basically, this is the received optical power that we have from in our receiver. As you can see, it decays quite rapidly. Oh, sorry. It decays quite rapidly with distance. So practically at 70 meters, we do not have anything resembling a signal to begin with. And in that sense, when we go to the next one, that's the SNR versus distance, we established a preemptive SNR minimum or SNR margin to say, well, this is, if we get a signal that has this SNR value, we may be able to get it working, because with a 6 dB margin, well, maybe if a fish comes through or if an algae patch comes through, maybe we have some lag in decoding the signal equally. And well, as you can see, it follows the exact same shape as the optical power. That's because they are directly related. And well, this I think is one of the most interesting parts, because it's the data performance. Here you can see in the yellowish plot the maximum theoretical capacity that theoretically, again, theoretically, goes up to 500 megabits when you are so close to the receiver and the transmitter are so close they can be practically touching. But when you go out of your way and add meters to the distance between both of them, this doesn't hold up so much, and you end up getting a lower and lower and lower and lower performance. But that being said, it's still enough to see Netflix underwater, for example. And although that's funny, with our modulation, we have to keep in mind that the actual binary rate that we can actually transmit is pretty much, well, is the lowest we can get, because OK is not particularly efficient with its information conveyance. So this sits about 20 megabits, and it stays roughly the same, so as stable as it can get. And it caps out when the capacity of the channel also bounds the upper maximum capacity. So, and the last one, that's the bit error rate, and pretty much in line with what we have seen already from the other presentations. We have a very good bit error rate figure just until we get to do the noise flow, and in that point, you can see the bit error rate just goes up to 50%, and that's just as good as getting a coin flip. So in that point, our transmission is useless. So you can see that with our model, as good as it gets, we can deduct what is the maximal operational range, and with the other figures, we can get how much data transmission binary rate we can actually get. And about improvements, another interesting stuff that we thought that was quite daunting to not put, because we put some thought on this. We are just going to cover this conceptually, because they are either theoretical concepts that we would like to implement in a future if provided more time, or they are complicated theoretical models that we could not manage to implement in the time that we're given. So in this sense, we had a Monte Carlo turbulence model that we do not put any trust in to say that there is a truthful representation of the turbulence, but it was a honest try. And we think that with more references, with more papers, and with more effort, we can get a somewhat decent result if we had months, maybe. And well, yeah, they are saying that I have to be faster, so we'll just end up with some of our future applications ideas. That's a swarm of robots, because if you keep them together, you can have a higher data transmission. So with that in mind, you can get better applications running underwater. And we would like to implement just some corrections if we had some algae patches, as I commented. Well, we just ignore this because it's just a theoretical concept about, well, when you have some temperature variance, your wavelength in the laser starts to vary as well. So we had an idea to maybe this was a good option to tackle. And that's all. Thanks. Sorry for the overtime.
Okay, great presentation. Now it's time for asking questions. No questions? Yes.
Okay, so thank you, congratulations. Nice presentation. So I have some remarks I think that you corrected that, but on the document you say that you use OK and are set. So.
Oh no, that's a typo. Yeah.
Yeah, I guess so. You talk about PPM also, but yeah, don't really
No,
get.
maybe we did that because, well, it was 4 in the morning, so the document maybe
Okay.
maybe
No,
had some
some.
typos. But of course,
Perfect,
the
yeah.
PPM we considered it, but it was too complicated to do it in the amount of time that we had.
Yeah, no, exactly. Okay, so yeah, you demonstrated really deep knowledge about the literature and such. So really nice. So the other thing, the block diagram that you present is not really what we were asking for. I mean, was really simple, but I would love to see, for example, some block diagrams on the LMS estimation that you have, because I don't really know if you understand what you are actually doing there. So I would love to see something on that. The hardware that you choose is fine, but I have a question. So you use a transimpedance amplifier. So you say that it has 80 megahertz of gain bandwidth product.
Yes.
So you have it there, and use a transimpedance of 10 kilo ohms.
Yes.
So that gives you 8 kilohertz bandwidth.
Yeah.
So the simulations that you have are really not
optimal.
No, not optimal. Are not even comparable with the hardware that you have. I mean, you have 8 kilohertz of. My voice has more bandwidth right now than the channel that you have.
Yeah, about that.
That's not bad.
Yeah.
Okay, but
yeah. If you want me to address that, we were looking about around in the papers, and what we seen that were so many different approaches. That it was so difficult to find just one compelling bit of information that was consistent throughout all of them.
Exactly.
So about that, that's all I can say.
Okay, and what on that time simulations that you have that are really nice, really, I love that. So, but what bitrate are you using? So what how fast are you transmitting?
Yeah, transmitting information. The binary rate we can achieve, like for example, at 50 meters distance, sits thoroughly at like 3 megabits per second.
3 megabits per second. Yeah. Okay. So that,
more or less.
For showing that, it would be lovely to have the channel capacity and the actual simulated channel capacity.
Yeah.
No, you have it, but if it was in log or in dBs, you will actually compare really nice. But yeah, like 3 megabits per second, 8 kilohertz of bandwidth, it's really impossible. But okay, that's all in all, I think it's really good work. Just some nuances, but congratulations, you did really well.
Well, thanks.
So I don't know if.
Yeah. Any further questions? Last question.
No, just a faster one. Again, here, are you using an external modulator or you're driving the laser?
Yeah, we thought about that, but we saw that it had much complications that we had not so much time to address. So about that, we thought about the internal modulation, that's the electronic one, or the external modulation. We compared them, but honestly, I think that due to our lack of understanding of the inherent trade-offs that we had, it's best that we kept this out of the presentation. So although we know that it existed, we decided not to put it in the slides.
Okay. Any questions?
Okay, so thank you so much, team number 4. A big round of applause. So yes, you can take seat. Thank you so much for your presentation. Congrats, guys. Congrats to all 4 groups. Now it's time for the jury to deliberate. We are at a point in our schedule where they need to go to another area to make their decisions. And as future decision-making people, you realize that now you are in their hands. And it's time, in the meantime, in order to give you some background on the photonics field, we have 2 amazing people. One of them you already know. And he's the first speaker, Dr. Raúl Esteves. he's part of SPAR right now. That's a foundry that was a spin-off of the QoPHI Lab. So we are extremely proud to see how ideas became reality. And that's what Professor Francisco Diaz did when he created Spark. So this is photonic field, is a field of expertise where is plenty of opportunities. So take this as a future vision of yourself in the near future. Raul, when you're ready, thank you.
Thank you, Miguel. So first, thank you for calling me a doctor, but I'm not a doctor. I wish, but no,
Researcher.
Well, yeah. So, where do I need to point?
Yes. Up and down. Go.
Yeah.
Now.
Okay. So I'm this guy. So I'm Raul. I'm a telecommunications engineer. I graduated last year, so not yet a PhD. I'm studying microelectronics in University of Sevilla right now, and I've been in Spark Foundry since last year. So, okay, so what's Spark Foundry? So we are a 3.5 semiconductor foundry for advanced photonics and RF devices here in Vigo. So we are one of the first, if not the first, company that wants to work and make an actual semiconductor fab, semiconductor foundry, and we are doing it here in Vigo. Our model, or what we actually want to do, is make an open access and pure play commercial model. So what this means is we will not be researching things, we will not be like doing the cutting edge photonic devices or cutting edge gallium nitride transistors, but we are more of a like pure play. We have some devices and people come here to fabricate and make them real. Okay, so right now we are on a startup or scale-up phase. We are more or less 25 team members, 5 nationalities. So the core people on Spark, we are actually from here, from Vigo. I'm from Cangas, and on the front, a lot of people from Vigo, from other parts of Galicia. But as we know, the expertise, the actual experts on semiconductors are not or are not yet here in Galicia. So we have a lot of people from Germany, a lot of people from the Netherlands, and a lot of people from the UK that worked on other semiconductor companies and on other foundries and have the actual knowledge to work. But as we'll see later on the timetable, we have a projection of more of 80 or probably more if we count all the operators and the people needed to actually run and make the wafers. So here we are talking about photonics. This is a photonics hackathon at the end, but we are more general than that. So what we want to do is work on 3.5 semiconductors. So 3 technologies mainly, I think I have it here, are indium phosphide. So a lot of you guys have already seen probably on data sheets and all of that you have modulators on indium phosphide. They're super fast. On gallium arsenide, this is more for maybe LEDs and super fast transistors. And on gallium nitride, that it's where I actually work. I'm in charge more of the characterization, testing, and all of that on gallium nitride devices. But the goal is to be able to work on these 3 areas. We actually have 3 reactors to grow these semiconductors separately because you cannot do it at the same time. So yeah, applications, whatever. I'm an engineer, I'm not a marketing guy, but this is more of a company presentation. But yeah, from LEDs to radar amplifiers to radio, telecommunications, fiber optics communications, millimeter wave, 6G, all of that you can do with 3.5 semiconductors. Okay, so here, I think this is the highest challenge. So you can see another fabs, mainly in the US, that get millions and millions and hundreds of millions of euros to make this kind of infrastructure. We don't have that. We have money, but not on that order of magnitude. So the actual barrier to make and build a foundry, it's really difficult. But on the other hand, we actually want, and Europe wants to have that resilience and that to be able to, instead of going to China to buy transistors and amplifiers for this, you can go to Vigo. So that's really nice for us. I will say that. So right now, let's say we just have an office. So we are doing European projects and we are doing research, but the core of the company is the actual foundry. So we need an actual space to build a clean room, to put the machines, and to make the chips. So we are more or less here. I will show you right now this video. I don't know if I can, whatever. But this is the actual, what it's now here. Okay. So this is in the PTL here in Valladares. It's close to here. This was like 1 month ago. So the foundation, it's there. This is last week. So here this will be the floor of the actual clean room where you need to go with the bunny suits and make the production. So we are there. We expect on end of the year, first quarter of next year, to have the actual clean room, to be able to go there and not fabricate, obviously, because it's a really, really long process of knowing the machines, trying, failing, and failing, and failing, and failing, and then have one wafer working. So the timeline is end of this year, or first quarter, have an actual building to be able to enter. That's it. Quarter 3, 4 have the operators there, trying and getting to know the machines and trying to get something going, and be able to produce on 2028 or half of that year. So we don't really know, but things are going well. So yeah, that's it. Thank you again to Alvaro for letting me be here and talk about Spark and the project. I think it's a really nice. I mean, I'm here 1 year. I've been in Spark for 1 year, but I've worked before here on the QoPHI Lab and things. And the project, I think it's a really, really good thing for Vigo and for the engineering here in Galicia. So yeah, thanks again, and you did a really good job, guys. I'm really proud of you. So thanks to all. Yeah. So right now we have an advisory of Spark, of the board of advisors of Spark. It's Liam Barry, and he will talk, I think, about the future of the photonics here in Europe and in the world. So go ahead, Liam. Thank you.
Just checking you can hear me okay?
Yes.
Okay, so let me just try and share some slides here and see if this works. I've had issues sharing slides recently. I don't know, so let me know if you can see my slides. Can you see a slide?
Everything is fine, Liam. Thank you so much for being here. Just for the record, Liam is one of the 100 top voices in photonics in the world. So, yeah, he's with us today.
Yeah, I mean, I'm not going to talk so much. I'm going to talk a little bit about history, maybe about where photonics comes from. Maybe some people know it. It's all very sort of historical, but I think it's good to it's good sometimes to look back before you can sort of look forward into what photonics can, potentially bring to society over the next decade and even over to the end of the century. Yeah. So I suppose it's good to obviously start off with defining what photonics is, and photonics is all about the science of light and photons and how they are generated, how they are detected, how they are manipulated through obviously emission, transmission, modulation, processing, etc., amplification, switching. So that's what photonics is. It's all about the science of light. And obviously we need to understand that light is, part of electromagnetic radiation, and where it sits on that electromagnetic radiation, if you look at specific wavelengths, you have all the way from low wavelengths of gamma rays and X-rays that you're all aware of what the applications are, to very high wavelengths where you have things like radio, for example. And then in between there, where you have wavelengths, of around a few hundred nanometers to a few thousand nanometers, you have what we call light, where we're generating radiation at specific frequencies where they can be seen. So that's obviously visible light. And then we have radiation obviously beyond that visible light, where we have what's known as infrared. And it happens to be the infrared that's primarily used for communication systems, for transmitting signals over optical fibers. And that's mainly because optical fibers tend to have a very low loss window, around 1550 nanometers. And that's why optical fiber tends to be used at that specific wavelength for transmitting signals over long distances. So, yeah, I mean, the internet, it's important to know the internet's obviously totally revolutionized the way everybody works, the way everybody lives, the way everybody interacts over the last probably 2 to 3 decades. And obviously the whole ICT, so ICT is what we call information communications technology, is a massive industry. And obviously it's totally dependent on the internet. So it's a huge employer in the European Union and globally, and turnover, the amount of money that's made from ICT is huge. So it keeps a lot of people employed, and from a European perspective, it's very, very important. But the internet, as we know it today, is currently under strain. And it's under strain for 2 reasons. First of all, we're all using more and more data. And secondly, there are more and more people getting connected to the internet. So although everybody in this room has probably been connected to the internet for a decade, maybe 2 decades, there are many parts of the world where internet connectivity is just starting. And so more people getting connected, and everyone who's connected wanting to use more apps, higher rates. We've gone from sending text to watching videos to sending videos to, sharing information between multiple people, videos between multiple people at the same time. So the internet is currently under strain with this massive growth in data traffic. And there's also a problem in terms of energy consumption. And energy consumption obviously is something that we're all concerned about nowadays. And although the typical energy consumption of our internet was typically quite low, as in 1 or 2% of the overall energy consumption, that's gradually starting to increase. And that's obviously causing problems. So we need to be developing new technologies that can be used to increase capacity, but also can reduce the energy consumption of our internet and the communications networks that we use. So it's always useful to think about what communication was like before photonics. And for this, I always like to use the first, I suppose, transatlantic telegraph cable that was laid. It's useful for me because it was actually laid from Ireland to Newfoundland in Canada. And this was installed in 1858. So if you imagine before, let's go before 1858, you wanted to send information between Europe and America, so the New World and the Old World. It basically took the length of time a ship could travel across the Atlantic Ocean. So, it took a long time to get that information. With the first transatlantic cable, suddenly you could get information sent in seconds, minutes, okay? And that totally revolutionized society because, people, for example, this is something from a newspaper written back in 1858, suddenly I can read the closing quotations from Wall Street on the same day, you know, and I can learn the prices in the Brussels grain market. I could learn the fact that Congress had readmitted Tennessee into the Union on the same day. So people could get information on the same day it happened. And that totally, obviously, revolutionized communication systems back in the 1850s. Obviously, we moved then from these transatlantic telegraph cables to a service that became radio-based in the 1920s. And then we had a transatlantic cable, another electrical cable in 1956. And then in the 1960s, we had two key optical inventions. So one was the laser and one was the optical fiber. And those key inventions then led to the development of optical communication systems. And we had the very first transatlantic fiber optic cable that could carry 280 megabits per second in 1988. Okay, and that was really revolutionary in terms of being able to send information across the Atlantic Ocean. And obviously I'm focusing here on the Atlantic, but similar developments were happening in the Pacific, and indeed fiber optic cables were being installed to develop terrestrial communications all across Europe, the US, Asia, etc. In 2020, the Maria fiber optic cable, we're now looking at 200 terabits per second. So the data rates you can see have expanded exponentially as we've gone through the last number of decades. And that's been thanks to many, many developments in laser sources, in optical fibers, and in optoelectronic systems. So like I said, we had two key inventions. The laser, people are probably, I'm sure everyone heard of a laser. Okay, so they're the two people who invented it, Charles Townes and Theodore Mammon. They obviously won the Nobel Prize in 1964. I always like to use this picture of a Goldfinger with James Bond because it was the first reference to a laser in society in terms of everybody in the street suddenly knew what a laser was when Goldfinger tried to kill James Bond with a laser source back in, this was something like 1967, 1968. And he was talking about a laser that could generate so much power it could burn through metal, which didn't exist at the time, obviously. So, you know, this is really people thinking ahead of what lasers could potentially do. So that was the first, I suppose, discourse of laser within society. Optical fibers invented also late 1960s, early 1970s by Charles Cow, and obviously he won the Nobel Prize in 2009 for developing optical fiber. So now all of our seas, Atlantic Ocean, Pacific Ocean, Indian Ocean, they're all crisscrossed with these optical fibers. And these optical fibers are essentially what keep us connected. And in addition to all of the submarine cables, we have many, many terrestrial cables laid across continents that basically keep us connected. And they are essentially the backbone of the internet, where the very high capacity traffic gets sent. Okay, so you know, there's many curves you can show to talk about continual traffic growth. It's been exponential for the last 3 decades. Here I'm just showing global traffic volume per subscription, so essentially per user. So think about how much information you use maybe on your phone subscription or on your subscription at home. You know, we've all gone from probably tens of megabits to hundreds of megabits. Now we're, you know, gigabits, and we're looking at hundreds of gigabits per month of information that we're using. So it's this continual traffic growth that means that we need to be developing new optical and photonic technologies that can support that growth. And like I said, can also do it in a reasonably energy efficient manner. Okay. In addition to obviously the internet, the other main area where we're seeing huge growth in traffic is in data centers. And these data centers are used for essentially storing information, and then obviously for sending information onto the internet. And these data centers are also used now for a lot of processing used for artificial intelligence. And that's why we're seeing huge growth in the data capacity needed in data center interconnects, both in connecting GPUs and servers within data centers that are maybe used for training artificial intelligence models, and also for connecting between data centers. So this is creating a huge demand for laser sources and a huge demand for optoelectronic components. So this is just showing, I suppose, that the datacom market now is really driven by the whole artificial intelligence, machine learning. We've a lot more complex models. The complexity of those models means that you need to be, you know, transferring information between your processors in your data center or your AI cluster. There's lots of information being transferred, and that's being transferred using optics. So you need to have much more capacity in your data center network. So we need more capacity in our data center networks. We need more capacity in our optical fibers that connect us up, you know, either with submarine links or with terrestrial links. And obviously, yeah, the main way in which we send optical fiber, or the main way in which we send high capacity signals over optical fiber is by using a technique known as wavelength division multiplexing. And we've talked about that in a moment, where we send multiple wavelength channels on a single optical fiber. It's important to understand that communications and bandwidth is very important. It's important, can be considered essentially like a natural resource. You know, you go back 100, 200 years ago, if you had oil, gold, you know, these natural resources, that's what really drove a country's prosperity. That's no longer the case. Now it's really access to information, and having really good internet is now key for any country in terms of economic growth. If you look at this is a nice curve just showing, I suppose, bandwidth usage worldwide, and it's scanning over 24 hours. You can see when you go red, you know, usage gets really high. When you go lighter colored, usage gets really low. And what's interesting is you can see there are still many parts in the globe where, you know, there's not that much internet usage. Okay, you go to Africa, for example. Think about Africa. There are, you know, huge population, you know, internet consumption very, very low. And even in certain parts of Asia, you know, where internet consumption is still very, very low. So there's potential, obviously, for that to grow, and that's one of the reasons why we need to be developing new technologies. So if you think about how you access the internet, you'll access the internet either on your phone or through a connection at home. And for those people old enough, you remember something called a dial-up modem, where we were getting connections of 10, 20 kilobits per second. So that was the connection we were getting maybe back in the 1990s. And we've gone from getting like 10, 20, 30 kilobits per second to 10, 20 megabits per second. And now many people can get, you know, gigabits per second at home. And you can even get hundreds of megabits per second on your mobile phone. In terms of the home usage, if you're getting a gigabit per second or more, that's probably because you have your home or somewhere where you live is connected very close to optical fiber. So the only really scalable solution to broadband access is having optical fiber installed to people's homes, because optical fiber has massive available bandwidth, and you can keep growing the data rate capacity that you deliver to people's homes by having fiber installed. This is a nice graph here from the European Union. It shows fiber penetration back in 2017. I don't know if I can actually put on a mark. Let me see if I can do this. I don't know, can you see a laser pointer? So if you see my laser pointer now, you'll see obviously even 10 years ago, there were many countries in Asia had already committed to go really like, let's install fiber everywhere to everybody. If you look here, Spain is at 24%. Ireland, interestingly, isn't even on this curve. It was at 0.5% back in 2017. Okay, so very, very disappointing. If you now look at 2026, where we are today, Spain is actually the highest penetration of optical fiber directly into people's homes or apartments in Europe. Okay, nearly 100% of people are connected. In Ireland, obviously, we're now up to 50%. Okay, and that's because fiber is the only way, you know, of having this really high capacity connection and developing what we call a digital society where everyone is connected basically all the time. Okay, so optical fiber is what's important, and obviously in Europe we've invested heavily in connecting people to fiber over the last decade. If we think about how very high capacity optical signals are sent, it's a very I suppose simple technique known as wavelength division multiplexing. Its analogy in RF is where you may be sending multiple information signals on different RF carriers, and that's called frequency division multiplexing. In the optical domain, we talk about wavelength division multiplexing. So essentially, each wavelength maybe can carry an information rate of 25, 50, 100, 200 gigabits per second, okay? And then you can stack up many, many wavelengths and send them all on a single fiber, okay? The speed at which we can send information on each wavelength is essentially dependent by how quickly we can modulate the optical carriers, okay? And we can modulate them either using intensity modulation, or we can modulate them using a combination of both intensity and phase modulation. The very first systems, they basically use very simple on-off keying. what that means is the light on is a 1 bit and the light off is a 0 bit. Very, very simple. We've moved over the last decade to more complex modulation formats, where we're now modulating both the intensity and phase of the optical carrier. And that means we can send more and more information on each wavelength. And if we stack more and more wavelengths on a single fiber, then we can obviously reach very, very high capacities. Okay. Yeah, so like I said, current systems now use both phase and amplitude modulation, and we also actually use polarization. So on each wavelength, we can send 2 polarizations over optical fiber, and then we can send both phase and amplitude modulation. So a typical modulation format might be something known as DP16 QAM, and that stands for dual polarization 16 quadrature amplitude modulation. Okay, it's quite complex, but what it means is that we're able to increase the data rate on each wavelength by using these more complex modulation formats. This graph is just showing, I suppose, the evolution of our wavelength division multiplex systems over the last 40 years. So the very first optical systems that were installed, they used a single wavelength, and that wavelength could carry maybe 155 megabits per second. Then in 1990s, we had the very first wavelength division multiplex systems. We had 4 wavelength channels, and then we gradually increased the data rate per channel and the number of channels in these systems. Okay, so we're now up to probably having 160 wavelengths on a single fiber, and each wavelength can carry maybe 400 gigabits per second. So you can see the total data rate per fiber has really exploded over the last 4 decades. Okay. But what that also means is that the fibers are basically becoming full from a spectral perspective. So, you know, we started off in the 1980s, we were using 1 or 2 wavelengths, and we'd lots of spare capacity in those optical fibers. As we've gone through the decades, we've gradually filled up the optical fibers, and that's why we've moved to these more advanced modulation formats like quadrature amplitude modulation, because we can send more information on each wavelength. If you look at one figure of metric we often use is spectral efficiency. That's how efficient are we using the bandwidth available in the fiber, and you can see that's gradually increased. And then the bottom, I'm started talking about the time it maybe takes to send a film over the internet. You can gradually see how that's, you know, greatly reduced over the last number of decades. Remember that the average download speed that you get, say, on your phone or at home, are orders of magnitude slower than the core capacity. So I'm talking about the capacity in our core fiber networks that form the backbone of the internet. The information sent on those core fibers is obviously aggregated from thousands, millions of users. So your average download speed is only a very small fraction of that. But obviously, as your average download speed increases, the total data rate in these fibers that form the backbone of the internet has to increase. Okay. This is a nice way of thinking about the internet and about wavelength division multiplexing. You can think about the bits of information a little bit like being people in a car where you're trying to transport them from A to B, okay? And you can think about the different lanes as more or less being the wavelengths. So how many wavelength channels have you available? And you can then think about the number of cars per lane as the data rate, okay? So you've got bits of information is the people, the number of lanes is basically the wavelength channels you have, and the number of cars is the data rate. And this maybe shows you what the optical fiber capacity looked like back in the 1980s and 1990s. We had maybe a few wavelength channels. We had a reasonably low data rate per channel, so not many cars in each lane. And we maybe had 1 or 2 people per car, okay? And what we've done over the last number of decades is gradually, you know, increase the data rate per lane, have more people in each car, okay? And what we then try and do is have more lanes, have more wavelengths. So this is where we are now. This is where we are today. If you think about the internet, it's basically full. It's like a traffic jam. So we've got every wavelength has its maximum capacity, and we can't really fit in any more traffic unless we start developing new technologies, okay? And one key technology that we can use to pack in more information on a fiber is a technology known as an optical frequency comb. If you imagine the problem with these cars on a motorway is that each car doesn't know where cars to its left and its right are, okay? We're not really using autonomous driving at the moment. So you have to have a lot of space between each lane to ensure there are no accidents. But if each car in each lane knows exactly where the cars are in the lanes adjacent, then you can actually pack those lanes a lot closer. And that means you can get a lot higher capacity in the optical fiber. Okay. So one way we can do that is by using a technology, like I said, known as optical frequency comb. So we need to obviously increase the data rate per channel and increase the number of channels. Just one important point to make here, I'm sure everybody knows it, but when we talk about a data rate, we're talking about the number of bits transmitted in 1 second. So some people who don't know much about communications, they often talk about, isn't it just the speed of light? But obviously the light travels at a certain speed, but the data rate is always related to the number of information, the number of bits sent in 1 second. Okay, so this is the technology I mentioned earlier on, optical frequency combs, and it's an area we've worked on in my university in Dublin for about 20 years, where we developed a technique where we can generate multiple optical carriers, wavelengths, from a single optical source. And what's important is the spacing between these optical sources is fixed. Okay, and because it's fixed, that means you can place your wavelength channels much closer together because they're not going to interfere or interact. Or if you think about it in terms of cars on a motorway, they're not going to crash. They're not going to crash into each other because they know exactly the position of the car in the adjacent lane. Okay, so optical frequency combs are a key technology for allowing us to increase the overall capacity in an optical fiber. Okay, and we've developed many technologies to build optical frequency combs. And about 15 years ago, we developed a company called Pilot Photonics, and that company now develops and commercializes optical frequency comb technology that can be used for increasing the capacity in both long-haul internet links, but also for data center links. Okay. Yeah, so this just shows one experiment that we did a number of years ago, where at the time this was the highest spectral efficiency in terms of the number of bits per second per hertz sent over an optical fiber using an optical frequency comb source that we had developed. So in this case, we're using about 14, 16 wavelength channels. We're using a modulation format known as dual polarization. We're using QPSK and we're using 16 QAM. I don't want to go into the details here of what the plots show. I mean, the plots are showing constellation diagrams, but with this optical frequency comb, we can place our optical channels much closer together in the fiber, and we can get essentially more capacity down a single fiber. So it's a key technology for increasing the capacity in the internet. And just to say, recently, 2 weeks ago, obviously the company is running now 15 years, so we got money from the European Innovation Council to scale up the photonic chips that we're developing, because there's obviously huge growth in the whole photonic sector. It's been driven by obviously more and more people getting connected to the internet, more and more people wanting to access more information, and the whole artificial intelligence boom is driving the capacity within data center networks. So photonic chips are really key for that. So just to conclude, obviously, optical communications is a key technology for high-speed internet and data center links. Growth in demand is really causing problems in terms of strain, both in terms of not enough bandwidth in the fiber, but also energy consumption. So we need to be developing new photonic technologies so we can have that continued growth in optical communication systems. So we need these new technologies, and optical frequency combs is one, and obviously all integrated photonic technologies will be key for developing these high-speed links that we need to continue the growth in internet bandwidth. I will say photonic technologies tend to have a very long maturation period. So, people have been working on optical frequency combs for the last 2 decades. They're now starting to become more prevalent for actual commercial systems. So technologies developed today, they may not have commercial value for a decade or more. Okay, and that's just the way it is in terms of photonic technologies. I will say an important line is, if you think about, I'm talking mainly here about communications, but obviously photonics and optics is relevant to many, many different applications, from transport to environmental sensing to medical diagnostics, etc., etc. And if you think about what electricity and electronics did for communications, transport, medicine, etc., etc., in the 20th century, light and photonics is having that impact in the 21st century. and will, I think, continue to have until the end of this century. So yeah, I'll stop there. I'm happy to take any questions, and I'll stop sharing.
Thank you very much for this insightful presentation, Liam. Is there any question from the crowd, from the students? Remember that you have Liam here, who is one of the top 100 photonic experts of the world. So if you have any doubt, now is the moment. Okay, thank you very much, Liam. They're so tired after this 48 hours working with no stops. Yeah. I hope they will send you a mail with some doubts.
Okay. Thank you very much. Take care.
Thank you very much. Please, mentors, have a seat. I will only ask you for a minute before announcing the final winners, all the results. I want to thank you, first of all, thank you, University of Vigo, Atlantic, and QoPHI. It's difficult to find people who wants to work with a lot of companies to create experiences that are useful for students and who want to do different things. I know that there's a lot of hackathons over there, but there's the first hackathon about photonics that we know about in Europe, and we need to start doing more and more about this kind of activities. So thank you all. Thank you to the mentors, to Vijay, to dedicate your time, your knowledge to the students, and to have so many interesting conversations. I saw them speaking about you guys, speaking about what every group need and how they can help you without revealing the solution. Having this kind of dedication with a large group of mentors, it's hard, and I'm really grateful for every one of you, and especially for you guys. As you know, for us, we organize this with a lot of care, and having 20 persons here working 48 hours, solving something that Alvaro will define as a pain in the ass, and learning about photonics is a great thing. Our goal here is not only to know about your ideas and solutions, but to make this more accessible and closer to you, because this technology, as Liam said, has a lot of future, and we need talented people who want to work with this. Your future, it's ahead, it's in the future, it's not now. You may work on this, you may not, but this knowledge is going to be relevant for your life, and I hope also that you get some friendships, some contacts, which is the really important thing. So, with this in mind, Alvaro, do you want to introduce the mentors? The mentors will get up with themselves. Okay, so thank you very much.
Yeah, so thank you very much, all of you, to coming to this hackathon. It has been like a really tough 3 days, I guess. Well, 2 days and a half for all of us, but now it's almost the end. And well, I'm gonna present you the jury, as I mentioned you the first days. We have, going from my side, from right to left, we have Raúl Estevez from Spark Industry, Spark Foundry, sorry. Yeah, you can come here, it's fine. Desiree González from QoPHI Lab, from the University of Vigo again. David Álvarez Soterello from the University of Vigo, Jojoyo. But also, I keep forgetting your surname. I'm sorry for that, but it is too tough. And if I'm not mistaken, of course, Javier, you're also part of the jury, so you can come here. Well, we're gonna go forward with the. Sorry? No, Omar, no, it's only 5 of you. Yeah. Oh, okay. I'm sorry, my friend. So yeah, we're gonna start going first with the best speech, going forward to the creativity, and then second and first prize, as you will know. So yeah, I will give it to you.
Do you remember the prices? Because it may be nice to remember the prices. The economical ones?
The economical ones. So, sure. Oh. Give me. Well, I don't have the presentation, but it's fine. We have the 4 different prizes. First, as I mentioned, the pitch is going to be individual. It's 100 euros for the pitch. The second will be the creativity one, or innovation, as they will call it. It's a group prize. It's, I think, 100 euros also for every single individual of the groups. Then going forward for the second prize, that is 200 euros per person in the group. And the first prize would be like 500 euros per person in the group. That's a lot of money. You can have a really great summer with that. So yeah, I will give the microphone to the jury again. And
Yeah, so it's for the best pitch. All the presentations were great, and thanks a lot for the participation, everyone. But particularly the group second stood out for the best pitch, Jai Zhou. Yeah, congratulations.
Now we will be continuing with Innovation and Creativity Prize. Although many of you presented great ideas, the jury has decided that the Innovation Prize would be to Group 2. So please get up.
Sí, ya pasamos.
Hugo. 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 Ah. Hugo, here. Sí, para ti.
¿Listo? Ok. So, que continúe Raúl con el segundo y primero, pues entonces. Ahora el segundo.
You go for the second.
Oh, that's fine.
Me. Okay. Well, and as the second prize, it's a pleasure to announce that is the Group 1. Yes, pictures for everything here. Momento incómodo número 2. Momento incómodo número 2. ¿Tú al final o qué quieres?
And now it's my pleasure to announce that the first prize, and please don't spend the money, spend it wisely, no alcohol, no vices. The first prize goes to Group number 4. Aquí tenéis. Lo repartís.
Creo que este es en Holanda, ¿eh?
Ah, bueno, pues esto es para mí. Sí, ¿esto es papel?
Enjoy. Well, we can give a big applause to the jury. It has been a tough day also for them. It's really actually pretty hard to qualify or to actually justify some of the parameters that we implemented to value you. But well, they actually managed to do it. So you can give a round of applause to them. And yeah, well, thank you for coming here. Thank you for University of Vigo and also Navantia Monodon for this chair and this event. It has been a pleasure to work with you and to actually be around here. And well, also Teltec from University of Vigo and all of the people who actually managed to organize this event. And yeah, that's it. I mean, if you want to have fun, we can go and grab some drinks outside and we can keep talking about the issues that you may be having and, I don't know, continue the discussions and enjoy. And